So welcome to day 4. We have now finished interstandard atmosphere category. Temperature, pressure, and density are behind us. So today we start a brand new category, basic fluid dynamics, and we are opening it with the continuity equation. Rho AV equal to constant. So this formula is really just one idea dressed up in symbols. A mass cannot appear from nowhere. So and it cannot vanish. So if air flows into a duct, the exact same mass has to come out the other end every second, no matter how the duct changes shape in between. This one simple idea explains something you have probably felt yourself. Why air speeds up when you squeeze a garden hose. So why a Venturi tube works, and it sets up tomorrow's formula, Bernoulli equation perfectly. So here is a formula. Rho AV equals a constant or written between 2 points along the same flow. Rho 1 A1 V1 equals rho 2 A2 V2. So rho is the density of the fluid in kilograms per cubic meter. A is the cross-sectional area the fluid is flowing through at that point. Think of it as the size of the pipe or duct opening, and V is the flow velocity at that point in meters per second. The subscripts 1 and 2 just mean two different stations along the same flow path. For example, the wide inlet of a wind tunnel versus its narrow test section. The quantity rho AV is actually the mass flow rate. How many kilograms of fluid pass through that cross section every second? So continuity just says whatever the mass flow rate is at the inlet, it has to be exactly the same at every other point downstream. So as long as the flow is steady. So now here is a simplification that makes this formula much easier to use in practice. For low speed flow, anything below about Mach point 3, which covers most propeller aircraft, cars, and wind tunnels, and everyday airflow. So density barely changes at all. So we treat it as incompressible, meaning rho is constant. When rho cancels out from both sides, the formula becomes much simpler. A1 V1 equals A2 V2. This is the version you will use almost every basic problem. And here is the intuition. If the area gets smaller, the velocity has to get bigger to keep that product the same. Use the pipe and the fluid speeds up. That's the Venturi effect. That's the Venturi effect. And it's exactly why a Venturi tube or your thumb over a garden hose makes water shoot out faster. Let's use this simplified formula on two classic aerodynamic examples, a wind tunnel contraction and a Venturi tube. Here is a worked example. A wind tunnel has an inlet area of 4 square meters where the air enters at 10 meters per second. It contracts down to a test section 1 square meter. So find the velocity in the test section. So step 1, write the incompressible formula A1 V1 equals A2 V2. Step 2 notes A1 is 4 square meters, V1 is 10 meters per second, A2 is 1 square meter, V2 is unknown. So step 3 rearrange for V2 equals A1 V1 divided by A2. So step 4 substitute V2 equals 4 times 10 divided by 1. So calculate, step 5 calculate 4 times 10 is 40 divided by 1 is 40 meters per second. So the air speeds up from 10 meters per second to 40 meters per second. A 4 to 1 contraction gives exactly a 4 times increase in speed. That's continuity in action. And it's exactly how real wind tunnels are designed to reach high test speeds. Now let's see the second worked example, Venturi tube. A venturi tube has an inlet area of 0.05 square meters, with air entering at 30 meters per second, narrowing a throat area of 0.02 square meters. For find the throat velocity, same formula V2 equals A1 V1 divided by A2. So substitute V2 equals 0.05 times 30 divided by 0.02. So 0.05 times 30 is 1.5 divide by 0.02, and you get the 75 meters per second. So the air accelerates from 30 to 75 meters per second through the throat. This exact principle is what old mechanical airspeed indicators and carburetors used. As velocity increases through the throat, pressure drops, which is precisely what tomorrow's formula, Bernoulli's equation, will explain. So three three mistakes to avoid. First, don't forget the incompressible simplification only applies below about a Mach point 0.3. Okay, for high speed or compressible flow, you must keep density in the equation. Rho 1, A1, V1 equals rho 2, A2, V2. So second, always match your area and velocity at the same station. Don't accidentally cross multiply A1 with V2. So third, sanity check. If the area decreases, velocity must increase, and vice versa. If your answer shows both increasing or both decreasing, you have made an arithmetic error. So go back and check. Now let's move for the recap. Rho AV equals a constant along stream tube. That's conversion of mass. For everyday incompressible flow, this simplifies to A1 V1 equals A2 V2. Smaller area means higher velocity. So your practice question, a duct narrows from zero point 0.1 square meters to 0.025 square meters with an inlet velocity of 8 meters per second. Find the exit velocity. Drop your answers in the comments. That's a continuity equation done. Tomorrow, day 5, we take this one step further with Bernoulli's equation, the formula that explains why that faster moving air we just calculated. And also has lower pressure, right? So Bernoulli's equation is mentioned here. A plus rho v squared plus rho gh equal to constant. See you then.